The first of the compounds we're going to use our understanding of atomic structure, etc., to explain the properties of are our ionic compounds. Now, ionic compounds are made up of cations and anions held together by ionic bonds. They are in a three-dimensional lattice, and to melt and then boil ionic compounds, you need to break these very strong ionic bonds. To dissolve ionic compounds in something like water, a polar solvent, the polar solvent has to surround each ion and attract it enough to remove it from the lattice, so to break multiple ionic bonds. Therefore, we can use melting point and solubility as indicators of the strength of the ionic bonds in our compounds. There are two things that determine the strength of an ionic bond. One is the ionic charge, so a 1 plus is not as strong as a 2 plus, and that is not as strong as a 3 plus. This is what we call a proportional relationship. As one goes up, so does the other. As the charge goes up, so does the strength of the bond. The other key property is ionic radius, how big the ions actually are, so therefore how close they are to the nucleus of the oppositely charged ion. This is an inverse or opposite relationship. As the radius gets bigger, the strength of the ionic bond gets weaker. And that sort of makes sense, because the further away those ions are, the less attraction there'll be between them. Just think of magnets. When we hold magnets near each other, it's harder to pull them apart, but if we start far apart, it's easier to move them away. Although this is an electric attraction, not a magnetic attraction, the idea is the same. So, I've taken a couple of examples to show you how this plays out. First one I've got here is where two sets of ions have got pretty much the same radius as each other, same radii. So sodium chloride and calcium sulfide, their ions have similar radii. The sodium ions are 102 picometers and the calcium ions are 100 picometers. That's pretty much the same. The chloride ions are 181, the sulfide ions are 184. That's pretty much the same. But what's different is the charge. Sodium and chloride are plus and minus 1 respectively. Calcium and sulfide are plus 2 and minus 2 respectively. Look at what this does with our physical properties. The solubility of sodium chloride is huge, 359 grams per litre at room temperature, whereas you can only get 0.2 grams per litre of calcium sulfide dissolved at room temperature. This infers that the bonding between these two ions is much stronger than between these two, because it is much harder for water to dissolve this, which means it's harder for the water to attract each ion sufficiently to break the ionic bonds. Whereas in sodium chloride, the bond must be a lot weaker because water can easily surround the ions, breaking the ionic bond. Also, look at these are melting points. Look at the melting points. 801 for sodium chloride, 2,525 for calcium sulfide. This is way higher. It's over 3 times higher. So this also reinforces that the bonding between the ions in calcium sulfide is stronger than it is in sodium chloride. And the reason for that is due to the charges of the ions, because the radii are pretty much the same. So we can remove that as a variable. This is showing the really big impact that a difference in charge has on the strength of the ionic bond. Now, the other thing we could look at is, okay, what if things have got the same charge, but their radius is different? What sort of effect does that have? So I've grabbed two oxides here, because then the oxides are going to have the same radius, same charge. They have got no effect on this. But magnesium is in the 3rd period, and barium, quickly racking my brain, I believe is in the 5th period. They're both in the 2nd group, so in group 2. So they're pretty similar elements, but their radii of their ions is very different. Barium's is nearly twice the radius of magnesium's. It has a larger nuclear charge, but that's not important now. It's the charge of the ion, 2+. Magnesium's is also 2+. Again, if we look at our solubility, 0.04 grams per litre for magnesium oxide. I mean, that's even lower solubility than calcium sulfide. So this has got really, really low solubility. For all intents and purposes, this is insoluble. Whereas nearly 3.5 grams per litre for barium oxide, that's much more soluble. So we can dissolve this, still not much, but we can dissolve this way, way better than this one. That suggests the bonding in magnesium oxide is way stronger than in barium oxide. The ionic bond is stronger here than it is here. This is supported when we look at the melting points. Magnesium oxide, 2,852 degrees Celsius. So nearly 3,000 degrees. And barium's 1,923 degrees Celsius is just under 1,000 degrees lower. So there's a big difference in melting points. Again, this suggests that the ionic bonding in magnesium oxide is stronger than the ionic bonding in barium oxide. Why? Well, if we look at the radii, this is why. The magnesium ions and oxide ions are packed more tightly together. They're closer together, so the impact or the effect of this +2 and -2 charge attraction is stronger because they're closer together to start with. Barium oxide, the barium's bigger, so it's further away from the oxide, so therefore it's a weaker bond due to distance. This is what we call inversely proportional. As the radius gets bigger of even one of the ions, the strength of the ionic bond decreases. These are the key things you need to be able to explain. If you are given a list of ionic compounds, you would break them up into their ions. You don't need to know their exact radii. You know ionic radii from the first couple of weeks of this topic, and you can infer using charge and radius, both ideas together, which of those ionic compounds would have the lowest and which would have the highest melting points or solubility or boiling points.